So our life in studying electrical circuits will be made easier if we stick to a convention which is encapsulated in the idea of a component. The idea is that all the physics that happens inside a black box, and we only need to know what shows up outside the black box. The black box in this case is the component, and the only access we have to it is the two leads that go into it and out of it, in which a current can flow, and the voltage that'll be developed from one side to the other. We'll stick to the case where no charge can build up in the component, which means that the current flowing in has to be the same as the current flowing out. So there's only one current, the current that flows through. And since there's no charge connected in the component, there can't be any electric field leaking out. Neither can there be a magnetic field leaking out. This is especially important for inductors, which we'll get to later. Capacitors, you might think, store charge, but they store positive and negative charges equally, so that they do conform to this convention of components that we have. So all we really care about in a component is the current that flows and the voltage that drops across it when a current does flow, and how big that voltage drop. Now, the voltage and current can flow in, we can label it as flowing in either direction or dropping in either direction, but we want to stick to convention. So I'm going to say here that the current is flowing in this direction. Might be a negative number, in which case the current is actually flowing to the left, but I have this freedom at the moment of saying the current is flowing in this direction. In that case, I'm going to say there is a voltage drop, but does it drop with the high side being on the left and the low side being on the right, or the high side being on the right and the low side being on the left? Well, I'm going to now have another convention, and this is one just of convenience, but if we stick to it, we will reduce confusion. And I'm going to say that the voltage always drops in such a way that the current flows into the high side, and then the voltage will drop, and when the current comes out, it'll have a lower voltage. Now again, we might end up with the voltage being negative in this case, but if we stick to this convention in our labeling, we will avoid a lot of uncertainties. So there are and so then once we have this convention, all that we care about in a component is how the voltage drop relates to the current, and we can think of that as a function of the current with respect to the voltage, or the voltage with respect to the current, and that will be some line as a function or pseudo function on this plot, as I've drawn here in red. And that function is the IV characteristic describing the component, and it tells us everything we need to know about the component. There are three components we will need to know about before starting in earnest on solving circuits. And the first of these is the DC voltage supply, which has this symbol, and it just shows that you have a high side and a low side with a given voltage. It'll be labeled with some voltage, 5 volts, 1.5 volts, whatever, and this is the high side and that's the low side, and that's the voltage difference between the two leads. Now, I have drawn a current going in here to the high side as usual. I expect that to be negative for a voltage supply because normally I expect the current to flow out of the positive side of the battery or voltage supply. However, no matter what the current does flow, the voltage difference doesn't depend on it, so I can draw the IV characteristic as this vertical line in that I always have the same voltage independent of whatever the current is. Another symbol that means the same thing is a battery. Like this, it's also a DC voltage supply, and an ideal one is exactly the same. Note that I put the large side of the set of lines crossing the leads to be on the positive side. And again, it has the same IV characteristic. It's identical in practice to a DC voltage supply. In the case of real circuits, if we actually have a voltage, a battery, we'll use the battery symbol, whereas if we have some, DC power supply with a voltage output, we'll use the round symbol. Another component is a DC current supply, and like the voltage supply, it provides a current rather than a voltage. So in this case, I will always get the current I, whatever it's labeled with, and it will be flowing in the direction of the arrow inside the circle. And so since it doesn't matter what the voltage is developing across it, I have that same current no matter what the voltage is. Again, like the DC voltage supply, I would normally expect the side where the current is coming out to have a positive voltage, but I'm going to stick for the moment with my convention and label the voltage this way. That V will normally be negative. Finally, there's the resistor. A resistor obeys Ohm's law, and Ohm's law describes a resistor. Anything that obeys Ohm's law is a resistor, including wires. They just have a very small resistance, and resistors obey Ohm's law. It's a kind of a tautology. But here's the symbol. Again, the current flows in, the voltage drops. In this case, they work together the way you would expect, in that the voltage will actually drop for current flowing in this direction. And here's the IV characteristic, in that the current is proportional to the voltage. If I apply more voltage, I get a bigger current. If I apply less voltage, I get a smaller current. If I put a negative voltage, I get a current flowing backwards. A bigger negative voltage, I get more current flowing backwards. The slope of this line, how much current I get for a given voltage, is the conductance, which I label G. Or if I were to take the inverse plot, the slope would be the the resistance R that labels the resistor. R is related to G as the inverse. 1 over R equals G. One final word about power. If you look at the units of current and the units of voltage and multiply them together, you'll see that you take coulombs per second for the current and joules per coulomb for voltage, and the coulombs drop out, and we get joules per second, which is a measure of power, which we can use watts. So therefore, if I take the product, current times voltage, I'll always get power. And in this case, it will always be, if we follow our convention, the power dissipated by the component. Therefore, in a resistor, if a current flows and a voltage develops, the circuit is dissipating power in the resistor. And because the product of I and V, you can convert one of those to R, or both of them, and you'll find that the resistance comes into that too, but it will always be dissipating some power. If the current is constant, the voltage is constant, it will be dissipating power at a given rate. This is the way a electrical heater works. You just put current through a resistor and it dissipates and it heats up from that power dissipation. For voltage sources and current sources, normally the current flows out of the positive terminal. In other words, the current or the voltage is actually going to be negative, and we'll get a negative power when we take the product. That means that voltage supplies and current supplies are actually not dissipating power, but adding power in the circuit, and therefore we're going to call both of those, voltage sources and current sources, power supplies.